Okay, so today we need to put on our 3D glasses because we're going to look at now expanding our knowledge of 2D moments to 3D. Now, with the 2D, we saw that there was actually 4 different ways we could solve it. What we're going to find is it's going to be a little harder in 3D. We're going to really kind of depend upon the cross product, although you can solve it in a scalar fashion, and we'll look at that a little bit. But what we're going to find is then we have some engineering body, the engineering baked potato that we always put up there and stuff. And there'll be some force out here that we're going to be interested in trying to understand what sort of torque or twist does that create about that point O. Okay, that has a line of action. Actually, we'll do that in green. And then we were talking about, even with the 2D, that we can draw some sort of a vector, R, what we call a position vector, your author calls a position vector, from the point of interest that we want to get this moment to some point on that line of action. And we'll just call that A. So it doesn't have to be at the force, but it has to be somewhere along its line of action. Now, one thing those two things do is define a plane. Sir?
Does the point A have to be at the intersection point of the circle? Because it's on the line of action, it's also along the perimeter of the circle.
Yeah, it could be over here. It could be down here. It could be out here somewhere. So it just happened to draw it there. But no, anywhere in the line of action is fine. And then what we'll do is establish some sort of a coordinate system with z coming out of the plane there, like so. So point O is our point of interest. This is where we want to find the moment, basically. And then just going what we said there, it's a point anywhere on that line of action. And then R is our position vector from point O to point A. And we can solve for that just like we did when we did the 2 points trying to solve for position, or for our, not position vector, our unit vector in the direction of the force and that sort of thing. So we can just simply solve it as just solve it simply as a vector. So this is a vector. It'll have a length. So it's in terms of some sort of a length. And we're not going to solve for a unit vector here. We're not interested in trying to find that unit vector. We're just interested in finding this vector. We need the full length there because, again, remember what we're going to do is then look for that perpendicular distance. And then finally, our force can also be expressed in terms of this same coordinate system. like so. And this will be in some sort of force terms, whether it's the SI system, newtons, kilonewtons, or pounds in the English system. And then as we say, R and F create a plane. So we actually kind of drew that picture there. Now, most of this will look pretty similar to what we did in 2D. We have a moment vector. Again, we're going to define this vector. And again, think about it in terms of that axis of rotation. But we're going to, in 3D especially, define it in terms of this cross product rule. We're going to find that's going to be our tool for getting things done. And remember, the magnitude then is going to be defined by this cross product rule. Where that angle theta is just simply that difference between the two vectors. Now, the problem is when we get into 2D, it's very easy. We can go measure that because we got it in a plane. When it's out there in some sort of space there at some angle and stuff, it's going to be kind of hard to kind of measure that. Key thing, though, is that then this is that same theta, which then, if we recognize the fact that equals this d, then we get back to that very definition that we talked about in 2 dimensions there. It's simply the magnitude, the multiplication of the magnitude of the force times the magnitude of that perpendicular distance to that line of action. And the tricky thing is then instead of having it stick out of the board or into the board and that sort of thing, if my F and my R are at some angle basically now, they're in 3-dimensional space there, again, we have this plane created by R and F. And what we're going to find then is that our moment vector is going to be perpendicular to that plane. Add yet another color here. So if I have a position vector and a force out here creating a plane like so, then my moment vector direction is going to be perpendicular to that plane. And again, think about it. When we were thinking about it in 2 dimensions here, we're going to rotate this way. It's again that axis of rotation. So even in 3-dimensional space there's going to be an axis of rotation created by a single force and that single position vector to that point of interest.
What's that other line you drawn there? Is that L or thing maybe, or right angle?
This one?
No, is that a right angle down there?
Oh, this is just, yeah, saying it's,
in the green?
In the green.
Green on the plane. We're kind of like that.
That's that perpendicular distance, remember, to the line of action. So that's D.
Okay.
Remember? So this is going back to that. We talked about that in 2 dimensions. That the nice thing about this is when we take the sine of that, that always is going to be that perpendicular distance. Okay. So wherever I measure it on that line of action, the angle changes, but it always basically gives me that same value, that D. Comfortable with that? We don't want to go too fast there. So now we've got this moment vector. Again, think of it as the axis of rotation that's going to be perpendicular to this plane created by the force and that position vector. And then finally, sing. Good. Yes, I want you all to sing. The sine basically is going to be the right-hand rule. And again, this is where engineers, you can tell the civil and mechanical engineers, because they're all doing this during exams. Again, if it's causing a rotation, I take my thumb pointed in the direction of the perpendicular, in this particular case, this way. If it's rotating with the curl of my fingers, then it's considered positive, counterclockwise. So if you look down that moment vector, it's going to be doing a counterclockwise twist. That's considered positive. If it's acting in an opposite sense, then it's going to be negative. So again, think about it. Get yourself in that position. Look down that vector, that moment vector. If it's going counterclockwise, it'll be considered positive. If it's twisting in the opposite sense, it'll be considered negative. Now, that's just to get a feel for it. The nice thing is when we get into that cross product, it solves that for us. It takes care of those signs for us. OK, so let's recall what we learned in this cross product. Bring our colors over here. Just to throw you physics majors off, I'm still going to draw my Z coming out of the board. And I will get my prop here. So Z is going to be doing this sort of thing. Now, what I'm going to be interested in doing is looking at a force somewhere out here now. So I'm going to draw it on the board here. Now, the nice thing about the force is then, since I've defined a coordinate system here, I can define that force now in terms of its x, y, and z components. So we'll get the prop out here again. So I've got this force that's out here in space, and it's pointing off in this direction here. I can define the proportion of that in the x direction, the proportion of that in the y direction, and the proportion of that in the z direction. So that's what we're trying to do with that particular thing. So it's broken up now into x and y components, and that's why we spend all that time trying to come up with that using the 2 points or angles and that sort of thing. We want to get it into x, y, and z components. We can manipulate it then. Now, if I want a moment here, and then we'll call this point O, that to draw a moment there, I'm going to need to draw a position vector to somewhere in the line of action. In this case, we'll just draw it to that point where the end point is, where it's actually being applied. Now, again, I can break that r component, that position vector, into x, y, and z components again. So what I'll see is an y component, an z component, and then an rx component. So again, to get to that position, if I were to go from O to that position, and I was going to go via this straight road, and this straight road, those are the three components, the three distances I need to cover in those respective axis distances to get there. So recalling what we did Okay, so recall we set up a determinant, and you could solve it by minors and whatever you're comfortable with, or you could just simply write the equations down, the three equations. So in terms of solving for, and this is MO of x, what we're saying is to get the x component of that, basically it's going to be these two pieces. Let's think about what that means then. So I've got this force out here. And let's think about our x component here. See, if you argue with me, I've got a long enough pole here I can take care of you. So let's think about this x component. So what we're saying is at point O, I want to know what the twist is about the x-axis. Okay, well, I've got this force out here, pointing off in some direction like that. Let's think about the x component. Is that going to do anything about twisting about O in the x direction, along the x-axis? That force is going that way, so is my x-axis. Parallel, not going to do anything. OK, let's look at the next piece. We have the y direction there. OK, well, now it's some rz distance away here. That's that piece here. So I've got a perpendicular moment arm here of rz, and I've got an fy component this way. OK, is that going to twist me about the x-axis? Don't all say it at once. OK, so it's going to rotate like that. Now let's think about sines. OK, I'm going to take my thumb pointed in the x direction there, and that twist is going to be opposite of my fingers, the curl of my fingers, right? When we think about that, that twist is going to want to go this way about the x-axis. So I'm rotating that way. Note then, that's where that negative sign comes from. Next piece, think about the rotation. I've got my force. I've got a z component now. Well, that z component has a moment arm now of ry. We think about that, so that will cause twist. It's going to twist me this way. Again, think about my moment, my positive moment. That will be in the positive sense. Come back to this equation. So there actually is a way of solving this scalar. And I want you to think about that. I mean, we can plug and chug stuff into equations, but think about what the pieces are meaning. So that's what that piece means, and we can do the same thing in the y direction and the z direction. And that's why we never see anything related to y there. It doesn't twist about the y. We don't see anything in the z portion there, because that doesn't cause any twist about the z. So that's basically when we plug and chug and go through this cross product, what it's really doing is just simply summing up all of those x and y components. It's very nice, it's straightforward. And again, the signs take care of it. Again, I said the f of y was going this way. Well, if f of y was negative, well, the negative will cancel with this negative. We'd end up having a positive twist. So again, the signs will take care of themselves as long as you pay attention to those signs. Make sure your position vectors are described correctly and your force is described correctly in the Cartesian system that you set up. Okay, so the next thing, we'll extend this. Okay, so what we're going to find is okay, this gives us a moment about a point. The moment vector describes basically that axis of rotation. Now the problem is think about this. This particular, we're setting up, well, let me draw the picture here. We've got this force. We got some point that we're interested in getting that moment. That defines this plane. And then my MO, moment about that O, is going to be perpendicular to that plane. Now the point is that when we start looking at structures and materials and that sort of thing, that doesn't necessarily, that may not be of interest to me. What I might be interested in is in a moment about some axis like so. Maybe that's something I'm welding two pieces together there. Again, this plane is just simply, it doesn't have anything to do with the structure. It doesn't have anything to do with the material. It's just simply a plane created by the fact that I've just drawn an r vector that way and an f vector that way. So in terms of getting to my real materials, or when I get into design and that sort of thing, I may be interested in actually what is the moment about that particular line, about some given axis. Now, a couple of things to note. There'll be some angle, generally defined by that. And what we're going to be interested in finding, now let's start drawing some of this. Okay, that's my perpendicular sign there again, shorthand there. So M naught is going to be perpendicular to this plane created by R and F. But again, as a designer, we're probably interested in looking at specific pieces. So what does that force create in terms of there? I might need to design my weld to resist that force. What we're going to do is then go back and find a unit vector. We're going to find a unit vector along that OL. And what we'll find then is that we can find the magnitude of that moment about that line, OL, by this weird little thing called the dot product. And I'm sure you're all read up and caught up on that. But again, this is the second way you can multiply vectors. We did the cross product, the more complicated one. This is actually a very easy one. So this is the tool then we use to basically then do this projection to determine the moment along this line OL, and then as a designer we can figure out how much weld or how many bolts we need to put in that particular phase. So we'll talk about this mathematical rule and how we're going to use it. Now the nice thing about this one, order isn't important in this particular case. So it's commutative, we can switch it around like that. Now a couple of things, you notice that I don't have an underline here. So the way this particular mathematical tool works is that's going to be a scalar. So it's going to give me the magnitude. But again, if I'm projecting it on OL, then I kind of know what direction I'm going anyway there, because I'm trying to get the magnitude of the projection of that moment on OL. Oops. So again, we'll go back to our picture here. I had drawn there a little earlier there. So my moment, I keep changing colors on you here too. My moment is in that direction there. I want to project it there, and there's going to be some angle here between those two vectors. And what we'll see is the difference between the cross product and the dot product is instead of a sine there, it's going to be a cosine. So it's the magnitude of this vector, OL, times the magnitude of the moment at O. So that's that perpendicular piece there, but it's the magnitude. And then it's times the cosine of that angle there. Now the nice thing is that this is any vector. So this is a strict definition, but what we're interested in is, since we are interested in OL, we talked about finding a unit vector. If this is a unit vector, what we get is that, because magnitude of a unit vector is that. And the nice thing is then when we see that, what we're seeing then, so when we do the cosine of that angle, basically, what we're getting now is a projection of that moment now on there. So it's just simply projecting the magnitude of that moment now onto that line there. So it'll be a little less than if it's some angle. If it's 1, it'll be the same. Anything else, it'll be slightly less. Now again, we don't necessarily want to go and measure angles out in space. It's a little difficult there. So what we want to do is use our rectangular coordinates. We want to solve all of our f's and our r's and everything in terms of x, y, and z components there. What we'll find then that it's actually a very easy expression. We just take all the x components, multiply them together, all the y components, multiply them together, and all the z components, multiply them together, and then sum up the whole thing. So a very easy calculation in terms of rectangular coordinates. Now noting that this is really direction cosines, right? So when we think about that, we've broken that up into those x, y, and z components. We've done that unit vector off into that direction OL. So this is going to be less than 1. This will be less than 1. This will be less than 1. But again, squares of those, sum them together, it should be equal to 1. So what we've done is calculated the magnitude of that moment about that line that we've chosen somewhere in space. But it's a scalar. It gives us a scalar product. But note that in order to get that dot product, we had to create this unit vector to get us there, right? We had to have a unit vector to project onto here to come up with that moment along OL there. So there's no reason, if we want to express this as a vector, we've already got the direction. We just simply, it's a scalar times that unit vector again. Nice thing about that. Then it breaks it up into the x and y, z components and stuff. So just to expand it, basically, in terms of what is the dot product then times the vector and stuff. So we solve for it in terms of the magnitude by defining a unit vector, and then we just simply multiply times that unit vector if we want to get it into x, y, and z components.
That equation you showed, so that last part is the same as the MO lambda OL equals.
Yeah, so this is really this here, right? That's just that scalar piece, this thing here, right? So we were able to, that solves as a scalar. Since that's a scalar, and we take a scalar times a unit vector, basically, it'll give us the components in the x, y, and z. Question?
Yeah, I guess I'm just having a hard time grasping what a unit vector is and visualizing what it is. Is it just a directional vector along OL with a magnitude of 1? Or?
Yes, yes, yeah, yeah. You remember we talked about that when we talked about 3D forces? Remember the very first thing we talked about was direction cosines? That's exactly what these are, direction cosine. So basically it's just saying I'm taking a vector, where's my stick? I'm taking a vector, I'm going to calculate that magnitude. When I divide the x component by the magnitude, what I get is the direction cosine. It's the cosine value. It's the percentage of the force or moment or whatever it is in that x direction. Same with the y and the z.
So that's what the unit vector is.
Yeah, yeah. And then it goes,
It's a fractional quantity of the component over.
it should be less than 1 unless it's pointing in the I, j, or k direction there. If it's 1, it can't be greater than 1. So you know you're in trouble when you get something greater than 1. And then if you take those and square those and sum them together, it's Pythagorean's theorem, which says it should be equal to the magnitude of 1.
So in order to find the, for example, unit vector of OL, would you take the x, say you're trying to find the unit vector of the OLX, would you just take the magnitude of the OLX and put it over the total magnitude? Would that give you the unit vector of OLX?
Yeah, you would calculate the vector OL by x of L minus x of O.
Yeah.
y of L minus y of L. So you get that vector. And then you do the Pythagorean's theorem to come up with that length. Like that. So you square each of those pieces, take the square root, sum them, and take the square root, and then divide. Just like we did with, remember with the 2 points going through? It's the same 3 steps there, the first 3 steps there. If it's for me, I'm not here. OK, so let's moment about, did I answer everybody's questions? Make sure there's no hands there. OK. OK, so there's going to be 2 approaches. We just talked about one, but we'll just kind of talk about what we just did. 1A, step 1A, OK, so what we did in our first step there is we went through and we solved for a moment at a point. So it's often a direction that's perpendicular to the r and the f. But it may not be in the direction that we're interested in. Now, one criteria we can't just solve for it anywhere. It has to be along this line that we're going to be interested in projecting onto. So we need to get it. We need to find that line, and we find a point there, and then solve for the moment using our cross product. We're all good at that. We can solve through that. And then 1B, OK. And then step B is then creating that unit vector OL and then using the dot product. So a 2-step process, and if you need to find the moment and that sort of thing, it's great, and then find the projection and stuff like that. Now, for those of you that are on the EIT exams and that sort of thing, if you need to solve for the moment on the line of action right away, there's going to be another process, but it's a 1-step process. It's called the mixed triple product. And what we'll do is kind of walk through that, and then we actually have an example we'll go through here in terms of solving it. And what I mean by direct approaches is that I don't have to go through 2 steps. I can solve for it in 1 step. So it's much faster. And if you're asked to find the moment along a line, I would suggest going that way. It's much faster than having to go through a 2-step process here where you do a cross product, then a dot product. And again, what this is just simply, if we have it in Cartesian coordinates, there's a very simple way of laying it out. So what we're doing is we're saying we're doing this dot product, but recognizing the fact then we've got this cross product piece here. What we find is what we're going to do is solve a similar determinant to what we did with the cross product. The only difference now is instead of ij and k in the top there, we're just simply going to put in those direction cosines. Everything else is the same. We have our position vector down here. And our force vector here described in terms of the x, y, and z components. OK, so that's basically it spelled out. But again, it's just simply solving this determinant, Rx, Ry, Fz. And then we go the opposite direction there, x, Rz, Fy, minus, because it's going the opposite sense. That's those two terms there. Then we move over to the y. If you want to solve it via the minors, you can do it that way. But basically, it's the same thing that we did with the cross product. But now what we're doing is we're solving for the moment along a line. And again, it's all done in one step, which is very nice. OK, so what we're going to do is we're going to go through an example, and we're going to solve moments along a line there both ways. And part of what we're going to be doing is solving for it at a point, which is then going to be your ability to solve it for a point anywhere. So that kind of gets us halfway through. And then we'll do the dot product. Everybody got this before I hide it? And this will be your handouts. So we'll just talk a little bit about it before we go to our screen. OK, so we're going to do 360. But I put 59 up there basically because we need some information from it, specifically the tension in the cables, which is 450. OK? So what we've been asked is to solve in 59 or in 60 is the moment about this diagonal AD. So it's along a line. And it wants us to solve it just for member BG. The other one had the other two pieces there and stuff like that. So we're just going to look at one force there, this force BG. And we're going to figure out its moment about that AD. And we're going to look at it two different ways. The first way we'll look at it is we're going to solve for the moment at this point here, A. So we'll solve for that moment. And again, it's going to be off at some angle. And then we're going to project it now onto that line. So it's, well, it's an equilibrium problem, but we'll get into that later. So what we've got is basically this bar here. We've got this single force that we're worried about. I know there's two cables there, and we're not solving for 59. We're just going to solve for that single force there. And we'll kind of walk our way through it. So we're going to use approach number one, which means that I'm going to solve for a moment vector at A. So you're going to have this tool to be able to solve for a moment vector at A. So the first thing we need to do is solve for this force, FBG. So we're going to go through. It's a two-step process. It's going to be that we're going to look at 2 points, and we're going to figure out that unit vector in the direction B to G. And then we're going to multiply times that force of 450 newtons. So BG, we'll think about it in terms of the x direction there. From G, it starts at 0 in the x direction and goes out to 5. You comfortable with that? So G's at 0, B's at 5 in terms of x. In terms of y, it starts off at 9.925 and comes down to 0. A slightly trickier one is K. G starts at 0.35, and then when we go back to B, it goes to 0.75. And basically what we have now is a vector describing BG. And that'll be in, what is it, meters. So that's basically the component directions from B to G.
On x, it's 0 minus 0.5, but then on the y, it's the minus is 0, so it's 0 minus.
OK, remember, this is the coordinate for G, right? So G's at 0.925, right? B is at 0. When we look at this one, G's at 0. You got it? Comfortable with that? Make sense? So it's always going to be G minus B in terms of establishing your direction. It's your choice of pointing. Again, it's a tension in BG, so we know the tension's pointing towards G, right? G's wanting to hold us up. So when we think about it, we want to go from B to G. So it's always the end point minus the beginning point. Just a general rule. Everybody comfortable? OK, next piece, we need to establish our magnitude. So basically, we just take those pieces square them. Take the square root of that whole sum. And your author's really good about making sure everything's nice in terms of. So that's basically describing the length of that cable. OK, 1.125. Now, what we're interested in is this unit vector BG. And then when we do and divide through it, I add those extra digits again for a little precision there. So I've created basically my direction cosines for this particular problem. And then to create my force vector, I just simply multiply it times that 450. So this is that 450 newtons that they gave us in that previous problem there. And now I've expressed my force from that cable, BG, the force at B, in the direction of G there in terms of x, y, and z components. And we, again, as engineers, you want to sit and think, does that make sense? Well, yeah, it should be negative, right? It's going in the opposite direction of the positive convention for x. It's going up. That's positive. And then in terms of the z direction, it's actually going back too. This is the magnitude. Remember that? Times a unit vector then, which gives us our vector in terms of FBG. So that gives us vector FBG. Doing on time here. OK, so remember our cross product. What we want to do is set up that little determinant. So calculating the moment, what we need now is an R vector. Can anyone see a nice R vector to B? No, it's from A to B, right? So what we want, A to B or A to G. Again, those are 2 points on our line of action that we can find real easily. Now, we probably want to do B because we can add a lot of zeros in there. Note that if I do R AB, it's just 0.5, a half a meter in the x direction. Now, we could do it at G, and actually, I want you to try that at home. You should get the same answer. But again, we try to find a position vector from my position A to one of those points on the line of action. The only 2 points I know are going to be B and G. I picked the simplest one there. But I can set up my MA now via our determinant. And this is what I like, zeros. Let's get as many zeros in there as we can, because then we don't have to worry about missing them. And then we're going to put our components of our force there. So unit vectors, position vector, force vector. Okay, so a couple things to look at. When we look at I, it hits a 0 this way, so it's not going to have anything. If I go the other direction, it's going to hit a 0 that way, so nothing for I. We go to j. If I go this direction, I'm going to hit a 0. Nothing there. If I go this way, OK, that's my negative direction, so I got a 0.5. And then I pick up the minus 160. When I look at k, if I go this way, it's going to be 0. So if I go this way, I'm going to pick up the 0.5. Oops, 185. And what I've done now is calculated the moment at A due to that force BG that we just calculated. Question? Got it? Yeah. Yeah, remember, if you're going this direction, it'll be a negative. So however you want to solve it in terms of, but it's just easy to remember it in terms of laying it out in terms of that determinant.